Okay, so question 3 of the Methods SAC 1 Mastery PDF. Again, if you don't have the PDF link in the description, we've also posted question 1 and question 2 walkthroughs as well. So this is question 3. This is a bit of a different type of question. This is more of an investigative type of question that involves the use of a parameter. And we can see in this case, we've got the parameter a. So the question is, consider the quadratic function with rule f of x is equal to ax squared plus ax plus 5. So what we have to do is obviously answer all these questions based on this, but presumably, because you can see that the start of part A, start of part B, it's talking about investigate. It's a unique type of question that's relatively new for the 2023 coursework. It requires more thinking, it requires more, I guess, abstract, and there's not just one way of working out. It requires more abstract thinking. So what we have to do is, obviously there's maths involved, but we have to think about the best way of displaying our solution and displaying this investigation, whatever it is, whatever the question is talking about. So you can see for part A, investigate the different amounts of x-intercepts f of x has. So we know how to find, or we should know how to find the different amounts of x-intercepts depending on our equation, but it's a matter of showing it in the most concise way possible. So what we have to do is think about, first off, how to find how many x-intercepts there are. And then based on that, we kind of like split them up into different cases. So we should know automatically that we have to use a discriminant for this one. So delta is equal to b squared minus 4ac. In this case, b squared is b is the coefficient of x, which is a in this case. So it's a squared minus 4 multiplied by a. The coefficient of x squared is also a, and then c is 5. So we have a squared minus 20a as our discriminant. Now, we just split it up into its different cases. So we know we can have two solutions, one solution or no solution, or two x-intercepts, one x-intercept, no x-intercepts. So we just say delta is greater than 0 for two intercepts. And then we'll do the working out from there. And then delta is equal to 0 for one intercept. And then delta is less than 0 for no intercepts. So it's a bit messy, but hopefully you can read it. Now this is how I would set up my working out, because I've got my clear 3 different cases and I'm just going to do the calculations for each of them respectively. So first off, we have a squared minus 20a is greater than 0. I could do this on the calculator, or I can do this by paper. I'll show you how to do it on the calculator. So if we take a squared, actually we'll just make it x just so it's a bit easier to graph in case we need to graph it. So if I solve this, what I get is x is less than 0 and x is greater than 20. And if you've got a graph of this, you can also just see where the graph is above the x-axis. So the intercepts are at 0 and 20 if you factorized it out. So you can see in this case, yep, 0 and 20. So you can see it's less than, would have to be less than 0, or x would have to be greater than 20 for it to be above the x-axis, which implies a y value of 0. So you can just say that in this case. So a is less than 0, or a is greater than 20. Sweet. And I might have to just include a statement for two x-intercepts. Sweet. And just be clear with the x-intercepts, don't just say intercepts. X is equal to 0 for one x-intercept. So we just say a squared minus 20a is equal to 0. And a lot of people would just put a equals 0 or 20. I think this is the trick with this question. If a is equal to 0, what happens? This becomes 0, which means we actually don't have a quadratic function anymore. So in this case, the implied domain of a is all real numbers because it hasn't said otherwise, but we have to exclude 0 because that's going to negate our quadratic nature of our function. So we have to reject a is equal to 0 since f of x is quadratic. Therefore, the only solution is a is equal to 20. I'm just going to box that. A is equal to 20 for one x-intercept. And then delta is less than 0 for no x-intercepts, so that's pretty easy. A squared minus 20a is less than 0. We've already done this before. It's just like the inverse of this one pretty much. So we just say 0 is less than a, which is less than 20 for no intercepts. This is really messy, but hopefully everyone gets the picture. I'm just splitting up into different cases and doing the calculations as necessary. And this would constitute investigation, okay? So it hasn't said specifically solve the values of a for let's say two x-intercepts, for one x-intercept, for no x-intercepts, but it's implied with the question that we have to cover all of those 3 cases because they are the 3 possible cases in this question. Now, B is also very similar. Investigate whether f of x has its turning point lying on either the x or the y axes. So again, we have this parameter a, and what I'm thinking is straight away, I just want to see if having the turning point on the x-axis or on the y-axis is possible, and if so, what are the equations, or what's the algebra involved in it. So we just obviously just start off with one or the other. I'm just going to start off with the x-axis. So if we have the x-axis, if the turning point lies on the x-axis, what does that imply? The y value of the turning point is equal to 0. Do you know what? After writing that, I just realized it's probably easier to go the other way around. Start off on the y-axis, because then you have your x turning point is equal to 0. And we most likely would go from x and then get to y, because x turning point, there's multiple ways of calculating it obviously, but the easiest way of calculating it in this case is x is when x is equal to negative b on 2a. So x turning point is equal to negative b on 2a. B is the coefficient of x, which is negative a over 2a. A is unchanged. Therefore, they actually cancel out, which you get x of turning point is equal to negative 1/2. Now, this is actually a very interesting result, and this is not really expected. What's actually happening in this case, it doesn't look too significant, but what this kind of calculation is implying is that the x value of the turning point is actually unchanged regardless of the value of a. So that obviously implies that the turning point never lies on the y-axis, because x turning point is always negative 1/2 regardless of the value of a. Yeah, that's actually an interesting result. Didn't expect that, but that's fine. It's important to note what your results actually mean as well. So that just comes with interpreting the algebra correctly. So if it lies on the x-axis, that just means the y value of the turning point is equal to 0. So what I could do is I could just do f of negative 1/2 is equal to y of turning point. And that makes sense because it's always equal to negative 1/2. If I had an expression in terms of a, I can just do that as well. So my equation is a multiplied by x squared plus a multiplied by x plus 5, I believe. Yep, cool. And I'm just going to substitute in x is equal to negative 1/2. And I get a minus 5 minus a on 4. I'm just going to double check that this is right. Let's see. I don't have any a defined, so that should be fine. Cool. Okay. Let's just double check my equations right. Yep. A squared plus x squared plus ax plus 5. Cool. So this is equal to 5 minus a on 4. And now if it lies on the x-axis, that means the y value of the turning point is equal to 0. So now I could just rearrange for a. So I get 5 is equal to a on 4. Therefore, a is equal to 5 times by 4 equals to 20. So a is equal to 20 for turning point on x-axis. And again, what I want to do is I want to double check these results. So I'll give you an instance. Let's say ax squared plus ax plus 5. I'm going to substitute in a is equal to 20. And I want to sketch it and see if it lies on my x-axis. The turning point lies on the x-axis, and you can see it clearly does. Cool. Sweet. And I'm going to check the y-axis one as well and see that the x turning point is always equal to negative 1/2. But I'm going to do that with the next question because I've already written the questions before. It's saying just investigate the general features and shapes. So obviously the turning point is part of that. The x-intercepts are part of that as well. So it says here that assume that a is in between negative 3 and 3 inclusive, and a is an element of z. That's an important thing to note because that implies that a can only be whole numbers. So the full possible set of a values, for this specific question, they've restricted it to just negative 3, negative 2, negative 1. We talked about before why a can't be 0, so it could be 1, 2, or 3. Now investigate how f of x changes in features and shape for varying values of a. So this is more general now. It's not talking about specific things. It's talking about just general features. We've talked about some already. We haven't talked about all of them. And the shape for varying values of a. So obviously I need to have some sort of calculations, but I'll also have to have some graphical representation as well. So what I'm going to do is I'm going to draw an axis. Hopefully we can see it amongst these lines, but I'm just going to draw my axes like that. Now what I'm going to do is I'm going to copy and paste my equation, and I'm going to take it to the graph and tab screen. We'll clear this. I'm going to paste my equation here. I'll tick it, and then I click the second button, which is the dynamic graphing button. Now what the dynamic graphing button essentially does is I can vary the parameter and it changes my shape, of course. So as I vary this, it's going to just change my shape accordingly. So what I want to do is I want to set the minimum to be -3, the maximum to be 3, and the step size of 1, because obviously these are all these are the only possible values I can have. And I'm just going to play around with it before I write down anything and just see how it changes and if it's kind of what I expect. So -3, you can see it's a negative parabola. -2, obviously it's a bit wider because the dilation has decreased in magnitude. -1 looks like that. And you can actually see that the x value of the turning point is actually never changing. The only thing that changes is the height of the turning point. I mean, when I say the height, I mean the y value. Cool. Okay. So it looks very interesting. What I'm going to do is I have to select cases to essentially investigate, or I have to select different values of A to actually investigate. Now, whenever doing this, you have to think about obviously your equation, but more importantly, what are the different features that you expect to change? For example, it makes sense to choose one positive number and one negative number at least, because at least you're covering like a negative and positive A value, which is going to cause a different graph, obviously. And then you should also select a pair of values that compares the magnitude of the number. So when comparing A values, there's obviously two ways that it can change. So you can either change in sign, or when essentially not just A value, but any number, it can compare in sign, or it can compare in magnitude, which is the same as like the size of the number. Like for example, if we had -1 and -3, that's a difference in size of 3. Right? So what I want to do is I want to pick A values that cover the difference in sign and difference in magnitude. So personally, again, there's no right or wrong answer. I think this is the best way, but you can choose whichever way you think is appropriate depending on how much detail you have to include. So I would choose 3 different cases. I would choose A is equal to 1 because that's just like a basic case. It makes the most sense to choose A is equal to 1 because it's just really easy to calculate things from. Then I would also choose the negative of that number. So I would choose A is equal to -1. And that would be like my sign comparison of A values. And then I would also pick A is equal to 3 because that's a direct comparison with A is equal to 1, A is equal to 3. That's a direct comparison of how the magnitude changes of my A and how that affects my graph. So I'm just going to pick these 3 cases and get the graphs up and compare the features. Okay. So let's pick A is equal to 1. You can see I've got a very basic graph up here. I'll go analysis, G-solve minimum to find my turning point, and I get -1/2 and then 4.75. So I can just keep it as decimals. You can see the whole number of decimals. So turning point is equal to -0.5 and then 4.75. Obviously, we have a y-intercept of 5, which that is unchanged because you can see it's not dependent on A. And you got no x-intercepts as well. So I just say no x-intercept, and then y-intercept is equal to 5. Now, if I change this to the -1, I want to see what changes. So let's see if the turning point changes. You can see it's translated up. So turning point is still at -0.5. X is equal to -0.5, but now we're at 5.25 for the y value. We have 2 x-intercepts. So I'm not going to solve them, actually. 2 x-intercepts because I care about like the features and the shape more so than like the specific numbers. 2 x-intercepts and like, yeah, the number of x-intercepts is kind of a feature. 2 x-intercepts and then the y-intercept of 5 again. Now I'm going to go A is equal to 3. So I go minimum to get the turning point. And we can see that the turning point is slightly changed again. It doesn't change too much, but it still changes slightly. And then we have no x-intercepts. And then y-intercept of 5. Cool. Awesome. So we've got all of our basic features right now. So what I'm going to do is I'm going to sketch them all based on the information that I just found and based on the graph. So I can see A is equal to 1 is going to have a turning point. Well, it's going to look something like this. Cool. Now A is equal to 3. The comparison is that the turning point is slightly lower. I'm going to use a different color, and I'll suggest you bring in different colors in the pen, different colors of pens as well in your SAC. it's going to be slightly lower, but it is going to be a bit of a narrower graph, which means that's why it starts slightly lower, but the y-intercept is still going to be the same. So if I just compare this and this, you can see that yes, the graph does translate down slightly when a is equal to 1. So when a is equal to 3. So when a is equal to 1, it's a bit higher, but then yeah, it's a bit wider. So I'm going to represent that somewhat like, so it's going to pass through here. It's going to pass through, I want to keep it symmetrical as well. It's not too much different, but it is significant enough to look something like that. Okay, it's not the best graph, but you can kind of see what's happening. Cool. And then a is equal to -1. The turning point is slightly higher again, but it's actually higher than the y-intercept, obviously, because it's dipping downwards now. But essentially, it's going to be the same shape in terms of in terms of narrowness and wideness compared to the green graph of a is equal to 1. So I'm going to try and reflect the same shape, but yeah, have it just like pointing downwards with a different turning point. Cool. And again, same y-intercept as well. Sweet. I think this is pretty good. So I've got a is equal to -1 for this one. And then I have a is equal to, which one was this one? This would be a is equal to 1. And then the purple one was a is equal to 3. This is a good graphical representation. I'll include all my turning points. So negative, let's zoom in actually. So the graph is really small. I should make, yeah. You should definitely make your graph big enough so you can actually write the values. Negative 0.5 and to 5.25. Cool. I'm just going to, you should actually write the full coordinate, but I got no space, so I'm just going to write y is equal to, because I know the x turning point, the x value of the turning point is just going to be the same. Sweet. Y-intercept of 5. And then, cool. Sweet. So I've got all my information summarized here. So I've got the different turning points. I've got the number of x-intercepts. I've got the y-intercept all the same. I guess, are there any other features that I need to include? Oh, maybe just wideness. So when a is equal to 3, that's pretty obvious, but we should just say narrower in comparison to a is equal to plus or minus 1. And then just say wider than a is equal to 3, and this one is wider than a is equal to 3 as well. By the way, I'm spending a lot of time in this, and it's because this type of question is going to be worth a lot more marks than the previous ones. I think I saw an actual SAC from a school, and this type of question was worth 8 marks, and the other types of questions, like these ones above, were worth like 3 or 4. So it makes sense that we have to spend longer on this. Just have to think, is there any other features? So we talked about x-intercept, we talked about the y-intercept, talked about the different values of the turning points. I guess there is a trend with the turning point values, which is as a goes from more negative to more positive, the turning point values actually decreases, like the y coordinate. So maybe I could just say that as a general trend as well. So as a increases from negative to positive, I'll just say y turning point decreases. Something like that. And it makes a lot of sense because we're going from a is equal to -1, a is equal to 1, a is equal to 3, and you can see my turning point is like slowly and slowly going downwards. So it makes a lot of sense to do that. Cool, I think that's all the features. Yeah, we talked about everything. No, I'd say that's fine. Let's move on to the next one. Okay. Now we want to investigate when it is possible to draw a tangent along f of x at some point. We don't know the point, it's at x is equal to b. But we want the tangent to pass through the point 3, 8. Okay, so this is what this is pretty much saying. It's kind of a unique question. So we have some sort of parabola. We don't know the shape of the parabola because it's still in terms of a. So it's in terms of a. We don't know the shape of it, but we know that we want the tangent at some random point to pass through 3, 8. This random point here is x is equal to b. So the coordinate would be b, f of b. Okay. So this is what this is pretty much saying. from a graphical perspective. Find the value or values of a for which there is at least one tangent on f of x that passes through 3, 8. Okay, pretty hard question, but there is a similar concept to this on question 1. Actually, we already went through it. If you've already gone through question 1 and watched the videos, you'll see that we use this concept of letting the derivative equal the gradient of the tangent with like a different expression. So what this essentially means is if we go back to this diagram, we can find the gradient of the sorry, I just went lost for a second. We can find the gradient of this tangent using our tangent is equal to y2 minus y1 over x2 minus x1, and then we could also let that equal to the derivative of f. And what that's going to get us is it's going to get us solutions for this point B. Now the only thing is, well, actually before I kind of jump to it, we'll try and solve this and see what we actually get. So what I'm going to do first is I'm probably just going to define this as f of x just to make calculations a bit easier. So I'll define it f, cool. So now when I calculate y2 minus y1, I could just do f of b minus 8 over b minus 3. That's the y2 minus y1 over x2 minus x1 with the coordinate 3, 8. I'm going to let that equal the derivative of f of x. So d dx of f of x. Now this, by the way, this is all going to be in terms of, the derivative of f of x at point B, I guess. Yeah, cool, that makes more sense. So we're going to substitute point B, which is just some arbitrary point, into the derivative, and then we can solve for B. So let's try this. I'm just going to maybe rewrite that working out as well. I'll just say f of b minus 8 over b minus 3 is equal to the derivative substituting b. By the way, the reason why I didn't just put b here is because what it's actually going to do is evaluate f of b first, which is going to be a constant, and then it's going to just differentiate the constant, which is going to end up being 0. So whenever we have to substitute a value into a derivative, we calculate the full derivative equation first and then substitute the x value on the outside, like what I've done here. Sweet. So I'm going to solve for b, and we'll see what we get. Before I solve for b, actually, I go to variable manager, and I have to actually delete a because I didn't have a defined before, but after I did the dynamic graphing actually saves the values of a, or saves the value of your parameter. So I have to go ahead and delete that. So we'll solve this now for b, and it shouldn't have any conflict. Sweet. So I have two expressions for b, which makes a lot of sense because there's probably going to be more than one value of b in some cases. But essentially, I don't care about that. It's just asking for the values of a for which there is at least one tangent. What you have to recognize, though, is that we'll just write down a solution anyway, and it's going to be a bit more easy to see how do we actually figure out what the value of a is going to be. So b is equal, you can actually see that the square root is exactly the same. It's just like the positive, like every part of the solution is exactly the same. The only difference is that just you got the negative outside of the square root compared to the positive. So I'm actually just going to rewrite it as 3 plus or minus the square root of 3 inside 4a squared minus a divided by a. I think that's it. Cool. Now, this is where kind of more intuition comes into play when coming up with the number of solutions. In this case, we're asked for at least one tangent, which is essentially just implying that we want at least one solution. So how I tackle this problem, again, there's multiple ways of tackling this problem. How I like to tackle this problem is from a more algebraic approach. So what I do is I see, okay, there's this solution that we have for b in terms of a. So what I want to do is, if I want at least one tangent, I essentially want at least one solution to b. Now, you might be thinking, oh, well, we already have two solutions for b, right? Not necessarily, because if you have certain values of a, which make this square root or whatever's underneath the square root negative, what happens to the square root? It becomes undefined. Therefore, you actually have no solutions. And this is a thing that a lot of people don't know, but it's a really important thing to note down, that if you want to find the number of solutions to something, you have to analyze the solutions and see, okay, when is the solution invalid? So in this case, we can say that the solution is not going to exist at all when this square root is negative. So we just do the opposite of that. If you want at least one tangent, what do you want? You want at least one b value. Now, how do we get, I guess, let's just say we want one tangent, right? We only want one tangent value, which means that we only want one b value. That happens when this becomes 0, which will mean that this, whatever's under this is square root, we will force that to be 0 as well. Now, what do you do if you want at least one tangent? Well, you can have one solution or you can have two solutions. So what you do for that is you say whatever's underneath the square root is greater than or equal to 0 for at least one tangent. Now, at least one tangent is just the same as saying at least one solution for b, because every b value is going to correspond to a different tangent. So hopefully that makes sense to everyone. If this expression, this is underneath the square root again. So if this expression was equal to 0, you would have one tangent. If this expression is greater than 0, you would have two tangents. This question is asking for at least one tangent, so we want to cover both bases. So what I can do is I can just solve this on the calculator. So I'm just going to say greater than or equal to 0. And I'll solve for a. So I highlight it, interactive, advanced solve. The calculator can solve inequalities. And I get a is less than or equal to 0, or a is greater than or equal to 1/4. But what I want to do is I just want to reject the a is equal to 0 solution because we can't have a is equal to 0. We don't have a quadratic function, same as the previous questions. So we just say I'll just say a is less than or equal to 0 for now. Union that with a is greater than or equal to 1/4. I'll reject a is equal to 0 as non-quadratic. And also you can see you're dividing by 0 as well, which doesn't make sense either. So therefore, a is an element of, I'm just going to put in interval notation as well, just for the people who want to use that, just for extra practice. Negative infinity to 0, exclusive. And then we union that with 1/4, and you can have it equal to 1/4 to infinity like that. Perfect. Pretty hard question. Hopefully people understand that. If you have any questions about it, leave it in the comments and we're more than happy to help you out. Part 2. Choose a positive integer value a that suits your part di solution and determine the b value that corresponds to the a value chosen and the equation of the tangent on f of x at this b value. And we've got a hint: if there are multiple b values for your chosen a value, choose the more positive value. Now, biggest clue with this question, never choose 1, never choose easy numbers like that, never choose 0. Just whenever you're asked to choose your own number for like an investigation question or investigation type SAC, do not choose easy numbers. Choose a medium number. Let's say like 3 or like 5 or something like that. So it's going to make it hard enough, so you're showing skill, but definitely don't choose 1 because it just doesn't like show any skill. And yeah, whenever you do calculations with 1, it always makes it a lot easier. So you kind of want to avoid that because you kind of just like, yeah, it's like the same as saying, oh, I'm just going to choose a parameter of 0. It just makes everything 0. And same with, it's very similar with 1. Everything just becomes a lot more basic. So we'll try and avoid 1 if we can. And in this case, yeah, choose any positive integer value that suits your part D solution. I mean, all positive integers suit this solution anyway. So we might as well just choose something like, I don't know, I'm just going to choose 4 in this case. But you can choose any value. So assume a equals 4, make it very obvious. I'm just going to box it as well. Just make it super obvious for the marker because it's going to be different for everyone. Sweet. Now, when a is equal to 4, we're going to have two solutions for b according to our solution above, which we already found here. So I'm just going to say, given x is equal to b, and then I'm also going to substitute in a is equal to 4, and I'm just going to find the same solutions. It's essentially just going to plug in a is equal to 4. So we get these two solutions here. But again, we have to choose the more positive one. I'm just going to write down both solutions first. Plus or minus 3 root 5 on 2. And I'm just going to say choose b is equal to 3 plus 3 root 5 on 2. Again, because it's saying the more positive value in the hint. And now I'm going to do all my calculations based on this number. Pretty messy, unfortunately, but yeah, that's the way it goes. Cool. Okay, so now we have our b value. Now what we can do is find the tangent of f of x at point b, this b value here. So the first thing I'm going to do is I'm going to take f of x, and I'm going to substitute in a is equal to 4, and that's going to give me the equation of f of x with this specific a value that I've chosen. And then what I'm going to do is I'm going to very easily calculate the tangent line by doing interactive calculation line and then tan line. So I could just substitute in the b value here. I'm just going to put 2 for now because I want to just replace this 2. it's very easy just to copy paste it rather than just type that thing out. So I'm just going to replace the 2 with that, and it's going to calculate my tangent at this b value. And that's all the question is asking. That looks very messy. Let's hit the simplify button, and we get this. Now, I probably want to expand it as well, just because I want to get it in the form y is equal to mx plus c. It just makes the most sense, and it's probably the most simplified. So I'll expand this, and then I'll factor out. Can I factor out x? I'll try it. I'm not sure if it actually works, but I'm trying factor out x. Okay, that factors x out of everything. Okay, that's not good. Let's just do it manually. I just say tangent y is equal to, so I'm just looking for the x terms here. So I got the first 2 terms as the x terms. So the gradient is going to be 12 root 5 plus 28x, and then minus 36 square root of 5 minus 76. This is really messy, but it doesn't really matter. You've got the calculator, so it's going to make it a lot easier. Now, there's a couple of things we can do to double check that we've done this right. The one thing that I'm definitely going to do is I'm just going to substitute in x is equal to 3, and then ideally I would get 8, and I do. So that makes sense. We've got the tangent line, which we just calculated, and I'm just double checking that when we substitute in x is equal to 3, we pass through 8, because that was the whole goal of the question. Yeah, there's other double checks that you can do. You can also graph it. Maybe we'll just graph it as well and just see what pops up. So this is my equation here. That's the tangent line, very steep. Let's get my equation when a is equal to 4. That looks like that. So you can see we've got that tangential point somewhat there. It's very steep. Let's zoom out. No, whoops. Let's zoom. I'm not sure what happened to my graph. Okay, let's go back to the main screen. Okay, let's sketch this tangent line again. Cool. Let's sketch this curve again. Cool. And let's just zoom out. So we can see that this is going to be a tangent line. I just want to kind of zoom into where they intersect, just so I can see. Okay, it's very steep, so it doesn't really matter. Cool, that's fine. We can kind of see that it is a tangent, but I guess we did use the tan line function, so we expect it to be right. But yeah, I guess this question overall was fairly difficult from an investigative standpoint. And this last question is a bit more like challenging from an algebraic standpoint. But whenever it comes to these questions, what I always tell my students is that the concepts when the numbers are hard are exactly the same as when the numbers are easy. So the best way of doing it is just like in your head, before you just jump into like, oh, how do I do this? Just think about how you'd solve the problem if you had a lot easier numbers. And then yeah, you just have to like apply the same process, but when the numbers are harder. And the process actually doesn't change. And for a lot of questions, the people answering the questions on a less successful, with a less successful percentage are usually just because the numbers are harder. But when you boil it down, the concepts are the same. So it's good to get used to applying the same skills with these harder problems, because the numbers are eventually going to be harder when you get to SACs and you get to exams anyway. But when you boil it down, it's the same skills that you guys already know. So it's just a matter of, you know, getting used to those more tricky and more difficult numbers that require the calculator to evaluate.